solving the sluice gate problem, homework number 4. A river goes underneath a partially open sluice gate. The system is considered two-dimensional, and the given in this problem are the velocity profile downstream of the sluice gate with a wall jet of velocity v21 equal 10 feet per second, and h21 is equal to 1.2 feet, and a reverse flow of height h22 is equal to 1.8 feet, and the velocity 2 is equal to 3 feet per second in reverse. The only thing that is known upstream is the height of the river, which is h1 is equal to 6 feet. The final goal is obviously to figure out the force per unit width on the sluice gate, but before that, because we know we're going to use the conservation of momentum, that's the only formula we have in our tools that deals with forces. We know that in the conservation of momentum, we need to have the momentum flux, because remember that the equation that we are interested in is this: the integral over the CV of rho v dv plus integral over cs of rho v v n dA is equal to sum of the forces. Now the problem was nice enough to give us the control volume, which is essentially just the entire domain all the way to here. Also, it's important to note that the flow is steady and frictionless. So there'll be no forces at the bottom. Alright, so question 1, determine the net flow rate per unit width of water across the control surface at region 2. So this is region 2, and I have this distribution of velocity. Now, how do I place my normal? Here I'm not considering a controlled volume, I'm considering a surface. Now I know that the bulk of my flow is flowing from left to right. So considering that the flow rate, the formula for the flow rate is Q is equal to the integral over the area of V N dA, I want a positive flow rate because I know again that the flow is going from left to right. So I am defining my normal going in the flow direction, and which by the way is the same as for the control volume, but I just want to make the point clear that really when we know which direction the flow rate is, we can define the normal in that direction. And so here, because the flow is frictionless, I have Q, according to my definition, the flow rate per unit width. So Q is equal to V 21 H21 So this is the positive part, okay? This is V21 here, and this is V22 there. Minus V22H22, and that comes from the scalar product, obviously. So I have 10 feet per second multiplied by 1.2, so 12 feet square per second, minus 3 feet per second times 1.8, and that comes to 6.6 feet square per second, so cube. This is my flow rate per unit width. So now in at section 1, at control surface 1, I have Q is equal to V1 H1. Again, in this case, I'm going to define the normal not based on the control volume, because the normal based on the control volume will be outward, but in the direction of the velocity. So Q V1 H1, so V1 is equal to Q divided by H1, which is 6.6 feet square per second divided by 6 feet, and V1 is equal to 1.1 feet per second. Alright, so now on to the real problem here, finding the force on the sluice gate, and for that we are looking at our control volume. And we are tallying up the forces. So we are again going to function in gauge pressure, since the entire system is at constant atmospheric pressure. So the first force, if we just tally up the forces, we have force of the water, hydrostatic force of the water upstream of the control volume on surface 1. We have similarly the force, the hydrostatic pressure force of water downstream of the control volume. We have minus F, which is the inverse of the force of water on the sluice gate, but really, because we are considering the equilibrium of the water inside our control volume, we have the force of the sluice gate on the water. So let's label all of this. Okay, so the total force of pressure, of hydrostatic pressure upstream, from upstream, is Fp1. The total force of the body of water downstream of the control volume is Fp2. We have minus F, the force of the sluice gate on water. And then, of course, we have our inertial terms that we're going to write right away. So the flow is steady. So again, I'm going to make a note here. Steady means d dt equals 0. So we are left with integral over Cs of rho v Vn dA is equal to Fp1 plus Fp2 minus F. Now let's break down the integral. First, let's calculate rho CS1 is equal to rho V1 dot N1. Oops, forgot to define my normals in here. So this is N2, this is N1, and we're going to decide that we're looking at the frame of reference IK, like this. So going back to my integral, the A, which is equal to the scalar product, obviously the velocity and the normal are of opposite direction, so the scalar product is negative. So I have minus rho V1 square H1. The integral of CS2 is slightly more complex. You need to break it down into two. So the rho in general form, it's rho V2 N2 dA. But now I need to go to the second slide, to another slide. The integral over CS2 is in fact equal to the integral over CS21 plus the integral over CS22, and that's equal to the integral over CS21, so that's the wall jet positive velocity with respect to the normal N2, so rho V21 square, so that's my 10 feet per second, H21 plus rho, made a mistake, minus, now we have the reverse flow, rho V22 square H22. Alright, so here this is the 10 feet per second, and here this is the 3 feet per second. Okay. Obviously H21 is 1.2 feet and H22 is 1.8 feet. So now we can assemble everything. FP1 is equal to 1/2 rho G H1 square I. P2 is equal to minus 1/2 rho G H2 square I, and obviously H2 is equal to H21 plus H22. So now if we assemble everything, we have minus rho V1 square H1, so that's the flux across S1, plus rho V21 square H21 minus rho V22 square H22 is equal to, I'm going to factor the force of pressure, 1/2 rho G H1 square minus H2 square minus F. Alright, so like here, I have forgotten a few things. So that's factor I. Here it's factor I, vector I minus F. It's important to keep the vector notation, otherwise we can easily get those. So F, the force that I'm looking for, is equal to rho G over 2 H1 square minus H2 square I plus, so this term goes on the right hand side if F goes on the left hand side, plus rho V1 H1. Well, I could have factored the rho. So rho V1 square H1 plus V2 2 square H2 2 minus V21 square H2 1. And here all of this is multiplied by I, and I just put it something wrong here. There you go. I. Alright, so when we replace all those symbols by their value, the first term here is equal to 837 pounds per feet, and this term, I believe, is hang on, minus, this term is minus 183 pounds per feet. So in the end, F is equal to 653 pounds per feet I. And so the force is indeed going this way. This is it.